So in last class we finished the combination definition as well, and we also see the intuitive definition, and we also derived the general one. So after that, let's study now the solved problem on combinations so that things become more clear. So the problem says that a committee of size 5 is to be selected from a group of 6 men and 9 women. Here maybe the committee spelling can be wrong, but let's ignore that. So if the selection is made randomly, what is the probability that committee consists of 3 men and 2 women? So in total, the target is to make a committee of 5 people, including men and women. And in total, we have 6 men and 9 women. So total, we have 15, right? So firstly, since we have to find probability, we need some sample space for the denominator purpose. So firstly, we have total 15 people in total, 9 women and 6 men. And at the end, we have to form committee which consists of 3 men and 2 women. So in total, we have to select 5. So from 15, we have to select 5. This is our sample space. Now, what are the number of favorable outcomes for this particular event? That is 3 men, 3 men and 2 women. So for that, we know that there are 6 men in total, and we have to select 3. So it can be done in 63 ways. And the same sorry for the but I have coughing since couple of days, so pardon me for that in between. And total we have 9 women, and we have to select 2 of them. So these are the ways of selecting 3 men out of 6 and 2 women out of 9 that we have. And of course we need probability, right? So the required probability is, we have to just divide by the total sample space, that is 15C5, which we calculated here, and we will get 240 by approx, it will be 1001. Yep, 1000 you can consider. So this is the probability that we will get. So we'll solve some complex problems as well. This was a really simple problem, but we will do like I'll make separate lectures in the playlist, and I'll add in between about the complex problems regarding permutation as well as combination, and thus the probability using all this. But we'll move forward to the theoretical part so that we can cover side by side theory as well. So next really important topic is conditional probability. And in machine learning, there is one of the algorithm called naive bayes algorithm, and it's really important. Already I have my lecture in my machine learning playlist. If you will go and watch, I'll also give you the link in the description, or you can select the I button for the same. But conditional probability is one of the most important concepts in statistics and probability as well as in machine learning. So let's understand it by going through an example. Firstly, we'll go through an example, and then we'll see the actual definition, how it is derived in an intuitive way. So let's say we are rolling a pair of dice, correct? And we all know that when we have pair of dice, then we have in total 36 outcomes, like 1 1, then 1 2, 1, and up till 1 6, and the same goes for 2 1 2 2. Then let me write just 3 1. I'm just keeping 2 1 2 2 row, but you can write if you want to. And okay, just to avoid confusion, I wrote it 3 2 3 3. I'm writing this whole until 3 6 because there is some reason. I'll take this an example, and then 4 1 4 2 up till 4 6, and the same goes for now 6 1 up till 6 6. So in total we have 36 outcomes, which we already know. When we throw a pair of dice, we have 36 in our sample space. But here now we have conditional probability. So firstly, let me frame our question, that what our question says. Our question says is that what is the probability that we already know that given a first dice has 3 on it, on the top, I mean has 3 on the top face. So this we already know, that on the first die here you can see that there is 3, that is fixed, right? So now our sample space will be reduced to just this 6 outcomes, right? rather than all 36, we just have now 6 outcomes in our sample space. So it is often called as reduced sample space. This is reduced because we already know that our first die is having 3 on the top, and that's the reason that our sample space is reduced. So the uncertainty that we had is reduced now. From 36 we just have 6 now, so we are more certain about this, and that's why it's called conditional probability, that there is a condition that is already fulfilled, that on the first die it is 3. But the question is that given a first die has 3 on the top of its face, then what is the probability that sum of the dice is equals to 8? And of course we can see that point here, 8 will be here only. So if I'll ask you like what is the probability, then we know that just one outcome is there which is favorable to this required event, that the sum should be 8 provided the first die has 3 on the top. So this is only one outcome, and out of not 36 but we'll just take 6 now. Why? Because our sample space is reduced, because we already know that our first die is having 3 on it. So all this rest of the outcomes, right, all this 30 outcomes, they doesn't matter, they have probability of 0, right? So I hope things are clear about this conditional probability stuff. Now let me just write in this way, that the conditional probability of this 30 points is 0, whereas the conditional probability of each of the outcomes, like this one, this one, this one, or any single outcome or each of the outcome, is 1 by 6, right? So this is what conditional probability is, that it reduces the sample space, and thus we are more certain about our probabilities or our result, that there is no much uncertainty about the result as compared to the unconditional probability that we have. Now most important thing is that how to derive the formula for the same. So let me go for derivation purpose. So now I'm going to the general case, having explained this uh, solved example or just an intuitive example of a dice, and obviously, like I just forgot to mention, but it's not necessary, I guess, that of course we have fair dice, there is no bias in any of the dice. Now moving ahead, that let's say we have now generalized case. So let's say we have two events, E and F. So what is event E? Event E is that the sum of dice is 8. It's the same example again. And what F says is that first die has 3 on the top. So then the probability that we obtain, that is 1 by 6 that we obtain, is called conditional probability of, this is really important, of E, that is what was E, like the sum of dice is 8, given that F, that is the first die has 3 on the top. So the probability of the event that the sum of dice should be 8, provided that the first die, that is F event, which denotes like first dice has 3 on the top, has already occurred and is denoted by this, that E, given that F has already occurred. This is a slash. So this is the notation that we will use, and it is also used in probability literature in all the books, if you will see. So this is the notation, but what can be the formula? Some of you might know the formula like directly, that it is P of E intersection F divided by P of F. But how? Like now we already know that P of F should be there, because from our previous example we know that we have to just check our reduced sample space. That is, what is F here? F is that first die has 3 on the top, and how many are there which has 3 on the top? They are just 6, right? So first die has 3 on the top, there are just 6 of them. So we already know that in the denominator, in our sample space, there should be P of F, correct? But how about the numerator? How we get this E intersection F? Let's try to think proof for the same, or an intuitive way, not the mathematical rigorous proof, but an intuition will be enough, right? So Again, I'm just trying to derive the general formula. This is just a Venn diagram for visualization, that this area is E intersection F, which we already know. So we have two sides E and F, and this is the area of intersection of the same. Now, general formula can be derived in the same manner just that we just described. That is how that if our event F, and what was F, you already know that first die has 3 on the top. So if my event F sorry, has already occurred, then it's really obvious that in order for E to occur, sorry for the spelling, occur, it is necessary that the actual occurrence should be a point in both E and F, because this is really intuitive, because from this example, if you will see that we know that F has already occurred, sorry, we know that F has already occurred. So now E event, which is sum, is should be 8, which is this case 3 comma 5, which is 8, 3 plus 5. This should be the point in both the events. It is already in the F, but it should also be in the E, right? So this means that this should occur in both of them. This is just a simple example that we just have one point in common, like this one here 3 comma 5, because our question says sum should be 8, but there can be some other examples that we will see later on, that more than 2 points are valid, right? So in that case, what we can do, we have to consider more than 2 points, but they both should occur in E and F, right? Here E just suggests that our sum should be 8, but they should occur in both of the event, not just single event. And thus the formula says that we have to write that in both E and F, which is, we call it E intersection F, right? And hence the probability that we wrote, that probability of E given F has already occurred, should be P of E intersection F and divided by P of F. I hope things are clear. So this is how we derive. So we just give, like, what is the probability, like that they are occurring in both, that is its intersection, divided by just the one which has already occurred. If we'll do this, we'll get the conditional probability that F has already occurred. What is the probability that E will occur now? So this is how the intuitive way of deriving things works. So I hope things are clear, and we will solve a thorough example on conditional probability in the very next lecture. So stay tuned. Thank you.